Our next speaker will be Eric Lerner. Eric is the president of Princeton Plasma Physics Incorporated. Eric's been active in advanced plasma focus research for over 25 years, starting in 1984. Starting in 1984, Eric developed a detailed quantitative theory of the functioning of DPF, or dense plasma focus. Based on this theory, he proposed that DPF could achieve high electron and ion energies of high densities, which would make it suitable for high energy fusion, advanced field fusion in space population. Eric is a leading researcher in cosmology and astrophysics. He's most recently been a visiting astronomer at the European Southern Observatories in Santiago, Chile. Eric's a writer about science and technology and is the author of over 600 articles. So welcome, Eric.
Thank you very much. So, we're talking about Fukushima as a black swan in a bad sense, an unexpected event. But there are also good swans, good black swans, that is, unexpected events that are good. And that's essentially what we need in the wake of Fukushima. Because Fukushima has very dramatically demonstrated to the world that we are in need of something we don't have, which is a safe, clean, cheap source of energy. Too fast. Now, there's several things about this that are pretty indisputable. A clean, safe energy source that the entire world can use does not exist. At the moment, for most of the world, the cheapest source of energy is coal, which has very major environmental disadvantages. This is the same situation that's existed in many parts of the world for the past 150 years. You go back 150 years ago, the cheapest source of energy was also coal. We don't know exactly how to get an ideal energy source. We don't know where this energy source lies, and although I'm a scientist and therefore very much an optimist, we don't know for certain if it's possible. So given that situation, how do we look for this black swan? The black swan of the good black swan of a viable energy source? I think the conclusion is fairly obvious, that if we don't know the path to it, we have to have a very broad-based research program, funded primarily by the government, that looks at many choices at once. Because if you don't know the answer, the quickest way to get the answer is to look at many choices at once. Now, to take thermonuclear fusion research as an example, which is what I'm involved with and what I'm most familiar with, the government's policy right now is very different than a policy of looking at many alternatives at once. The vast majority of the government's resources in research in thermonuclear fusion are actually in just two approaches. In fact, two projects. One is the International Tokamak Experimental Reactor, ITER, located in France, which is a huge magnetically confined device, many times the size of this building when it's constructed. This is the construction site right now. And the other is the National Ignition Facility lasers, which is an equally huge collection of lasers, which is constructed and operational. So basically almost all the eggs are in these two baskets. There's a concentration on just one fuel for nuclear fusion, which is deuterium and tritium. These are two isotopes of ordinary hydrogen. Tritium is itself radioactive. These are huge, expensive, very long-term projects, not expected to go to commercialization before the halfway point of this century. And they're far from ideal. because this reaction produces its energy in the form of neutrons. Neutrons have several disadvantages. First of all, the only way you can get energy, we know how to get energy from a neutron, is to use them to heat up water for a steam cycle, turbine, the way we've been producing electricity since Edison. This is quite expensive in itself. And neutrons also produce induced radioactivity. So at present, we don't have a broad-based policy. We have a very narrowly based policy, which I think is pretty much the case in other fields of research as well. What this means is that many alternatives that could be a faster route are being overlooked. To be more specific, I'll talk about one alternative we're involved in, which is using different fuels, aneutronic fuels, fuels that don't produce any neutrons. If you can have a thermonuclear reaction, that is a nuclear reaction occurring at very high temperature, that produces only charged particles, the motion of those charged particles can be converted directly into electricity by sort of a high-tech transformer, potentially leading to a vast reduction in the cost of electricity. In the case of this reaction, hydrogen boron, a proton, which is the nucleus of hydrogen, and boron 11, which is the most common natural form of boron, combine at very high temperature to very briefly form a carbon nucleus, which instantly breaks up into 3 helium nuclei. Main thing about this, no neutrons are produced. All of the particles produced are charged. That means with cheap and abundant fuel, you can get a direct conversion into energy. It's safe and no radioactive waste is produced. It does have a drawback. You need enormous temperature to produce this reaction. The energy of the ions have to be over 100 keV, which is the same as more than 1 billion degrees. That's 100 times the temperature in the center of the sun. So, in a way, these alternative fuels have been considered ugly ducklings. But without looking at the ugly ducklings, we can't find the black swans. And in fact, there are ways to achieve such enormous temperatures. One alternative, which not only we have been working with in our lab in Middlesex, New Jersey, but other groups of researchers have been looking at, about 40 groups around the world, is a device called the dense plasma focus. The dense plasma focus is an extremely small device. This is a picture of our device in Middlesex. For scale, this is about 8 feet across, and the electrodes are a few inches across where the reactions take place. A generator in conception would be not much bigger. This would be not only small, cheap, it would also be distributed energy because the average generator will produce about 5 megawatts of energy. It's enough for a small community. This device has already achieved the temperatures necessary to burn hydrogen and boron. We haven't been using hydrogen and boron yet, but we soon will. And this little device already produces more energy output per unit energy input than the giant NIFRI experiment out in California. It's not a working device yet. We need much greater density to burn the fuel fast enough to get more energy out than in. But this project's very economical. At the moment, we've got a budget of $600,000 per year, and we estimate $40 million for full commercialization. Just to give you an idea how this works, this is how we would get the energy out. Basically, the energy comes out in the form of a beam that goes into a coil that's then fed into energy storage devices. And energy also comes out in the form of X-rays that are converted directly to energy. There's a little animation that shows these DPF in action. These are the electrodes Thanks, Doug. These are the electrodes that are only a few inches apart. And what happens is